We sit on the couch, tap a screen, and a high-definition movie instantly begins to play. Our laptops sync terabytes of data in the background, and our smart speakers answer questions in real time. We expect this digital infrastructure to be entirely seamless and invisible. But if human eyes could perceive the radio spectrum, that peaceful living room would look like a blinding, turbulent storm. We are constantly swimming in intersecting electromagnetic radiation. Every inch of that space is bombarded by signals piercing through the drywall. Frequencies from the local cell tower, microwaves from the kitchen, overlapping signals from your neighbor's router, and a dozen smart devices in your own home screaming for attention at the exact same time. In an environment this loud, a laptop pulling a perfectly sequenced 4K video stream out of thin air is like trying to hear a single whispered conversation in the middle of a packed football stadium. Wi-Fi functions as an active, highly choreographed system, enforcing a precise negotiation that prevents the airwaves from collapsing into total electromagnetic chaos. Looking at this telecommunications station, you can see the macro-scale hardware origins of radio broadcasting. Modern wireless networking relies on this exact same physical mechanism, high-frequency radio waves transmitting energy across a distance. Inside your phone or laptop, the internet exists purely as digital information, a microscopic sequence of ones and zeros. To move through the air, those digits have to be converted into rapid pulses of electrical current. This animation shows what happens next. A tiny transmitter inside your device pushes that current into an antenna, broadcasting it outward as an alternating current. The digital ones and zeros are now a physical wave oscillating through space. A uniform, repeating wave doesn't convey any information on its own. To actually transmit those ones and zeros, the device performs a process called modulation. By modifying the width or the height of the wave as it pulses, the device encodes the specific binary data directly into the physical shape of the signal. Physics provides the vehicle to move energy across the room. Yet, if dozens of devices pump out modulated waves simultaneously, the resulting collision of frequencies is mathematically useless to the receiver. To make sense of that physical energy, the local network requires an anchor. That is where the router comes in. The router acts as a physical translation bridge. One side is plugged directly into the global, physical internet via fiber optic or copper cables. The other side relies on an array of antennas facing the wireless edge of your home. It operates as a highly specialized traffic cop, simultaneously taking in the chaotic airborne requests from your laptop, television, and smart thermostat, translating them back into digital data and routing them out to the wired internet. The internal processors of that router can parse billions of bits a second, but that raw computing power is entirely useless unless every device in the room agrees to speak the exact same language before they start transmitting. To ensure devices from entirely different manufacturers can communicate, engineers rely on strict global networking standards. Organizations like the Internet Engineering Task Force and the IEEE write the protocols that dictate how devices must behave in the airwaves. As shown in this diagram, the first rule these protocols enforce is separation. The overall radio frequency band is sliced into specific lanes, or channels. If your laptop and your neighbor's router are trying to talk at the same time, the protocol forces them onto different channels so their physical waves do not overlap. The second rule is a strict order of operations. Devices do not hold a continuous connection. Instead, they slice their data into tiny packets and negotiate turns to transmit. Your laptop asks the router for permission to speak, sends a packet, and then goes silent to let the smart TV have a turn. This rigid process of stopping, asking permission, transmitting, and waiting happens millions of times every single second. It is so fast that it creates the absolute illusion that every device is connected continuously. The hardware generates the radio waves. To make those waves useful, the software protocol applies an invisible architecture, forcing a highly disciplined cooperative conversation onto an otherwise chaotic physical medium. Zooming out from those microsecond negotiations in a single living room, you see this exact same process repeating across the entire global IT infrastructure. We have taken a naturally wild, rapidly oscillating physical energy and successfully bound it to the strictest possible digital laws. Because these standards are universally applied, they scale endlessly. Billions of isolated local networks operate side by side in apartment complexes, office buildings, and cafes across the world, all managing their own traffic without collapsing the surrounding airspace. The simple act of playing a video triggers a hyper-fast, invisible coordination of waveforms and global standards, a massive, silent architecture that keeps the modern world connected.